Welcome back to the deep dive. So for years, the best LLMs, the really massive cutting-edge ones like GPT-5 chat, they've all been behind these proprietary expensive APIs.
Right, they hold this massive, multi-billion-dollar knowledge advantage.
But what if you could teach a much smaller open source model all the intelligence of that giant without ever seeing its internal code?
And that is the core question we're answering today. This is the definition of black box distillation. We are diving into a Microsoft research paper that outlines a really revolutionary technique called generative adversarial distillation, or GAD.
Okay, so knowledge distillation, KD, is sort of the AI equivalent of having a genius mentor teach an eager student everything they know.
Exactly. And the result is a smaller, cheaper, faster model that ideally retains the performance of the enormous teacher.
But the black box setting, that makes that direct mentorship pretty much impossible. It does. So our mission today is to unpack GAD. This framework solves the problem by transforming distillation into this clever minimax game, an adversarial setup that's specifically designed to enable sophisticated on-policy learning.
Even when the teacher model is completely locked down.
Right. And the stakes here are huge because the paper shows that GAD enables student models to achieve performance that is, and this is the key phrase, comparable to the proprietary GPT-5 chat teacher itself.
That is the headline we are drilling down into, the democratization of high-end intelligence. So let's start by clarifying the playing field, this distillation dilemma. We need to understand the difference between the ideal scenario and the one we're actually stuck with.
For sure. The ideal scenario is what we call white box distillation.
White box.
Think of it like this. If the teacher were a person, you'd have access to their full brain scan. You would see every thought, every probability they assign to every single word choice.
So in the AI world, that means the student has full access to the teacher's hidden states, its token logits, everything.
Everything. The full probability distribution.
So if the teacher is thinking of 3 possible next words, say cat, dog, or mouse, I don't just see the final word cat.
No. You see that the teacher assigned maybe a 60% probability to cat, 30% to dog, and 10% to mouse. You see all the alternatives it considered.
And standard white box methods just align the student's probabilities to match that full distribution.
Exactly. It's a clean, direct, and very effective transfer of knowledge.
But the most powerful foundational models are proprietary. They're API models. You're paying for a service, not the source code.
Which forces us into the black box distillation scenario.
The real-world headache.
Yeah. Now, all you see is the final text response. You don't know why the model chose that word or what it thought about the words it didn't choose. All that rich information is just gone.
And the conventional methods for black box, things like sequence-level knowledge distillation or CKD, they just treat the teacher's response as a perfect gold standard answer.
They do. They just train the student to imitate that single text response. And, while that sounds reasonable on the surface, it severely limits the depth of knowledge that gets extracted.
It's like learning history by only reading the final summary paragraph of a chapter.
That's a great analogy. You miss all the context.
And this brings us to a concept the research really emphasizes as crucial, on policy learning. Why is learning on policy so important for creating a really high-performing student model?
Well, on-policy learning is fundamentally different because the student learns from his own trial and error. It's not just learning from the teacher's fixed examples.
Okay.
Imagine you're learning to drive. CKD is like reading the driver's manual and only seeing pictures of a perfect parking job.
Right.
On-policy learning is like actually being in traffic, making a mistake, and having an instructor instantly tell you, you turned the wheel too sharply, here's how you correct it.
So it's that immediate, tailored feedback based on what you just did?
Based on your current generated response, yes. And that's what's missing in the black box world. And studies have shown this is vital. It reduces something called exposure bias.
Where the model just gets stuck in patterns it saw in the training data.
Exactly, and it promotes what's called mode-seeking behavior, which leads to much more robust performance. But to get that instant feedback, the student needs some kind of reward signal right after it generates its own response.
Which you just don't get from a standard API call. GPT-5 chat only gives you the final string of text. The API is basically a black hole for any of those internal metrics.
A total black hole.
We should probably also quickly mention the other big reason you might need black box methods, even with open source models, the tokenizer problem.
Yes, that's a good point. Sometimes the student and teacher use fundamentally incompatible tokenizers.
A tokenizer being the map that turns words into numbers for the model.
Right. So if the teacher uses one map and the student uses a completely different one, their internal numerical representations of the same text just won't align.
They're speaking different numerical languages.
Precisely. So you can't compare their internal probabilities or logits directly. Even if you could see the logits, the numbers wouldn't mean the same thing. You're forced back to just comparing the final text output.
And you need a way to assign a quality score to that text, a reward.
You need a text-only, sequence-level quality score.
Okay, so this is where the innovation begins. The situation is practically screaming for a workaround, and the researchers delivered GAD, generative adversarial distillation.
Right, and this framework enables that on-policy learning using this brilliant adversarial setup.
So let's unpack the two players involved here.
It's a two-player minimax game modeled on generative adversarial networks, or GANs. It's a game of deception and detection.
Okay, so player one, the student model. This is the generator.
The generator, or G, is our student LLM. It gets a prompt, what's called $6, and it generates its best possible response, GGOS.
And its goal is simple: fool the system.
Just fool the system. It wants to produce responses that are absolutely indistinguishable from the proprietary teacher's output. It's trying to forge a perfect copy of GPT-5's style and quality. And player two is the discriminator, the judge. The discriminator, D, is trained to be a world-class authenticity expert. It takes the prompt and a response, and it outputs a single score, a quality score.
And it's trained specifically to tell the difference between the teacher's real response and the student's generated attempt.
Exactly. And the genius here is that it's trained using pairwise preferences.
Meaning it learns which response is better, not just if a response is good or bad in isolation.
Correct. The paper mentions they use something related to Bradley-Terry loss, which is just a fancy way of saying the discriminator is trained to always give a significantly higher score to the real teacher response.
When it sees them side by side.
Right. This mathematically forces it to learn all the subtle stylistic and quality differences.
Okay, let's pause on a technical point here. We have this great adversarial game, but GANs are, they're notoriously unstable and hard to train. Why didn't this whole thing just collapse?
That is a highly critical question, and it's where they leveraged a specific technique from reinforcement learning.
Oh.
See, the student generates text through a sampling operation, which is non-differentiable. You can't use standard calculus to backpropagate errors, so they treat the problem like a classic RL task.
So the student isn't trained by gradient descent in the normal way. It's more like it's playing the game, getting a score, and then adjusting its strategy based on that score.
That's it exactly. The student, the generator, is trained using policy gradient methods. The paper says they use GRPO in their experiments. And crucially, the discriminator score is simply treated as the reward.
So the student updates its policy, how it chooses its next words, to maximize that expected reward.
And that's how they enabled on-policy learning. The student gets immediate, high-fidelity quality feedback on its own newly generated responses.
So the discriminator isn't just a static judge. It's more like a co-evolving coach that gets better at spotting flaws as the student gets better at hiding them.
That is the key innovation here. The discriminator acts as an on-policy adaptive reward model. In traditional reinforcement learning with human feedback, RLHF, the reward model is trained once and then it's frozen. That's a recipe for instability and what we call reward hacking. GAD avoids this because the discriminator co-evolves with the student policy through the entire training.
It stays sharp.
It stays sharp, providing stable and dynamically adjusted supervision.
This sounds incredibly powerful in theory. So let's get to GAD in action. You said the results were astonishing. What did the data actually show when you compared GAD to the simpler CTAD baseline?
Well, the setup used GPT-5 chat as the teacher. The students were a range of open source models, 3 billion, 7 billion, and 14 billion parameter models from the Qwen 2.5 and Llama 3 families.
And across the board.
Across every single benchmark and model size they tested, GAD consistently and substantially outperformed CTAD.
But the finding that really stopped me in my tracks was the performance of that Qwen 2.5 14B student. This is where it gets really interesting.
Oh, yes. The Qwen 2.5 14B Instruct model, after distillation with GAD, achieved performance that was statistically comparable to the proprietary GPT-5 chat teacher itself.
And that was on the LMSYS chat automatic evaluation,
which is a highly respected benchmark. It uses average scores generated by another cutting-edge model, GPT-4o, to judge the quality. It's a very tough test.
Just think about that implication for a moment. You took a proprietary, massive, closed-source model, And using only its text output and this adversarial framework, you taught a freely available open source model to mimic its performance almost perfectly.
It's a huge step. It's a huge step toward leveling the playing field in AI.
And it wasn't just about high scores on the training data, right? The real win was in generalization.
That's right. The most significant triumph was the robust out-of-distribution generalization. They tested the distilled models on datasets that were not part of the distillation process at all. Datasets like DALI, Self-Inst, and Vicuna.
Because if a model generalizes well, it means it learned the principles of the teacher, not just the specific answers.
Exactly. And on these crucial tests, CKD really struggled. In some cases, it yielded only marginal gains or even negative improvements.
So the distillation actually hurt its ability to handle new tasks.
In some cases, yes. It had overfit to the training data.
But GAD?
GAD maintained robust performance gains on all these difficult, unfamiliar benchmarks.
Okay, so why? Why the massive difference in generalization between the two methods?
It all comes down to the core learning behavior, which the researchers categorized brilliantly as mode covering versus mode seeking.
Let's break those down.
Okay, think of CKD as a photocopier. It's a mode covering model. It tries to assign some probability to every possible teacher-like output, spreading itself thin just to cover all the teacher's exact phrasing.
So the data showed it had a high n-gram overlap. It copied the exact sentence structure.
The exact local word choices, yes. But the final quality score was low. It copied the words, but it missed the overall style.
So it's just memorizing vocabulary and sentence patterns, which leads to overfitting. It's brittle when it faces something new.
Right. GAD, on the other hand, is a mode-seeking model. It's like an art student learning the master's technique.
Okay.
It doesn't obsess over copying every single token perfectly. It concentrates its probability optimization on the highest quality, most reachable regions of output space. It captures the teacher's global stylistic characteristics, the tone, the structure, the depth.
That leads to true knowledge transfer.
And far superior generalization. The quality of the style is more important than the exact words chosen. GAD learns the inherent quality signal, not just these superficial text patterns.
Which brings us back to the stability we talked about. That adaptive, co-evolving discriminator must be the secret sauce here, because what happens if you freeze the reward model, make it off policy?
Instability, and it happens fast. When the researchers tested an off-policy approach, where the discriminator was trained once and then frozen, the student model exhibited severe reward hacking after only a few hundred training steps.
And reward hacking is when the student just learns how to game the system to get a high score, even if the output quality tanks. What did that look like?
It started producing excessively long responses.
How long?
Sometimes ballooning up to 1,300 tokens long. Responses that clearly deviated from the teacher's style. It figured out that the frozen discriminator was biased toward rewarding length, and it exploited that vulnerability relentlessly.
It was just generating nonsense to get the maximum score.
Absolute nonsense. And it just underscores why that dynamic adversarial loop is so critical.
Because the GAD framework, by continually updating the discriminator, prevented that.
It prevented it entirely. It remained stable through thousands of steps because the quality target was always moving, always adapting to what the student was trying to do.
Yeah.
You can't game a system that's constantly learning your cheating strategies.
Before we wrap up, there was one necessary step the paper emphasized, the warm-up stage. This sounds vital.
Oh, it is. Before the adversarial game can even begin, both the generator and the discriminator have to be warmed up for a single epoch.
So you fine-tune the student with standard CKD for a bit, and train the discriminator on that initial difference.
You do. Because if you skip warming up the generator, the student is so bad at the start that the difference between its output and the teacher's is just gigantic.
The discriminator can instantly tell the difference every time. The game is too easy.
It's too easy, the interaction is meaningless. And if the discriminator isn't warmed up, it's too weak. It can't provide any useful feedback. It's basically guessing.
So the generator gets no useful reward signal.
And its improvement stalls. The warm-up just balances the playing field so the game is competitive and informative right from the start.
So what does this all mean for the future of AI? GAD is this incredibly effective and robust framework that uses a generative adversarial setup to extract high-quality generalized knowledge from closed-source LLMs like GPT-5 chat.
And it achieves state-of-the-art results, even parity with the teacher, all without needing any proprietary logic access.
It confirms that generalization ability in these models is really tied to the learning process itself.
It is. The ability to use on-policy learning techniques, especially those based on reinforcement learning, provides superior, non-overfitting generalization compared to just static, supervised fine-tuning. The power is in the process, not just the data.
So if we connect this to the bigger picture, GAD really validates this idea that even the best-kept proprietary secrets can be, in a way, reverse-engineered simply by observing their behavior. And this raises an important question for you, the listener, and for the entire market.
Yeah?
As a black box distillation methods like GAD become more common and more effective, does the proprietary advantage held by the largest foundational models simply become a temporary head start rather than a permanent, unbreachable barrier to entry? That is the real disruption.